Okay, we're going to do lots of examples where we go ahead and find these places of concavity. Remember that concavity occurs at the second derivative. So that's what I'm going to start out by doing. I'm going to take the first derivative, and then I'll take the second derivative, and the second derivative is negative 6x plus 6. We're looking at where the second derivative has possible points of inflection, so where it does not exist. There are no values where it does not exist or where it is equal to 0. Solving for x gives me x is 1. We're testing these possible points of inflection for the second derivative. We want to know what's going on with the second derivative. If the second derivative is greater than 0, if it's positive, then we know it's concave up. If the second derivative is negative, meaning less than 0, then we know it's concave down. So let's test this interval. Let's put 2 in. Let's say we have negative 6 times 2 plus 6. That gives me a negative value. And then right here, when I plug in 0, I have negative 6 times 0 plus 6, which gives me a positive. So that means my interval of concave up is from negative infinity to 1. So it is concave up here because the second derivative is positive. It is concave down from 1 to infinity because my second derivative is negative. This next example, we are going to find the second derivative. I noticed that this will be much easier to take the derivative of. Rather than using a quotient rule or chain rule, let's just change this into 2 cosecant x. Take note of the interval we're looking at. We're only going from negative pi to pi. So we're going to go ahead and find the first derivative. That gives me 1 plus 2. The derivative of cosecant is negative cosecant x, cotangent x. And then we'll go ahead and take the second derivative. Second derivative just ends up being, the 1 is 0, so we have a product rule right here. I'll underline my first and second part. So I'll say first times the derivative of second. The derivative of cotangent is negative cosecant squared plus cosecant x times the derivative of the first part there. So it would be negative 2 cosecant, back up. The derivative of cosecant is negative. So I'll have negative cosecant x cotangent x. Well, this will simplify to give me a positive 2 cosecant cubed, because I've got 3 cosecants. A negative times negative 2 is a positive 2. Plus, I have negative 2, and then inside of here, actually that changes to positive, because then negative 1 times negative 2 is a positive 2. I have a positive 2, and I have 1 cosecant x, and I have 2 cotangent x's. This will simplify further. What I can do is factor out a 2 cosecant x. That leaves me with cosecant squared x plus cotangent squared x. This actually equals 1. This is one of the reasons I picked this problem, is because it's a little bit more difficult. That equals 1. And then I'm going to go ahead and write my second derivative as 2 over sine x. Now remember, our goal was to find the possible points of concavity. So I want to look at where it is 0, which this second derivative will never equal 0, or where it does not exist. So where it does not exist is when the sine of x is equal to 0. Well, the sine of x equals 0 when x is 0 only. So it is, I can write undefined at x equals 0. That's my only possible point of inflection. But remember, I'm only going from negative pi to pi, so I only need to test these particular intervals and see what's going on with the second derivative. Remember, everything entails a second derivative. So when I plug in pi over 2 in for here, at pi over 2, I end up with a positive value. And when I plug in a negative pi over 2, I end up with a negative value. So it is concave down from negative pi to pi, or negative pi to 0, and concave up from 0 to pi. So it's concave down here and concave up.